I'm Andy Weyenberg. I run the aftermarket performance and motorsports division for Miller Welders. So today I want to go through some aluminum welding. We kind of do an aluminum series pretty much every year, but we mix it up a little bit. So what I'm doing this year is talking about the different alloys, some of the applications for those, some of the best ways to fabricate it, and of course some filler metal selections and welding applications. Okay, so with aluminum, you've got a lot of stuff going on outside of steel. With steel, picking filler metals and things like that and fabricating it seems to be a lot easier than aluminum. With aluminum, there's a lot of different alloys and they have some of their special applications. So just take these two pictures for example. There's a lot going on here, right? So if I take this one, I've got a radiator. And the radiator has the 3003 side tanks. It's got a 50-52 top and bottom, and it's got 60-61 fittings, right? So you got a lot of stuff going on there, right? So what happens is you're in different applications, so you have to pick the proper filler metal. So a lot of people, and I'm not going to blame distributors or things like that, because when they'll sell stuff, because the customer walks in and says, I need some aluminum filler. So they'll sell you a generic aluminum filler. But in reality is the filler metals need to be selected based on the application. And there's a lot of different criteria on that. And so I'll talk about that too. So on this one, we've got a 3003 pressurized overflow tank. This is a 60-61 filler, and you got 60-61 fittings on here also. So again, 3003 to 60-61 is a wide range of an alloy. So let's look at some of the characteristics. 3003, I love working with it. It's easy to bend, it's easy to fabricate. And it has some pretty good strength, believe it or not. And even to anneal it, it actually anneals at a much higher temperature than some of the other aluminum alloys. So I do a lot of my fabrication with 3003. This is a tank that I make. Some of you might have seen some of this before because you've been here a couple of times. So this tank I make out of 3003. And it's a power steering tank, and I make it because it goes inside my down bars in the engine bay, and it fits right in that nook there, and it gets it out of the way. So I like making these because it's a specific application for what I'm doing, and it gets stuff off the motor. You know, if you go buy a tank, you're bolting it or securing it to something, and it's in the engine bay area, it's in the way, right? So I get a lot of people that want to start doing this stuff, making custom tanks. So this is 3003. It's easy to form. I put some bead rolls in it. It's easy to weld. I've got a 60-61 fitting with my cap on it, and of course my fittings for my hoses, right? So on this one, we're going to pick the application because it's in an engine compartment and I'm working with hot fluid. One of the primary things I'm going to look at for this is picking a filler metal that's applicable in high temperature applications. So 50-52, it's stronger, it's harder to bend, which is okay, but it also has real good memory. So when you look at like aluminum racing seats, come on now, get back here. So if you look at aluminum racing seats, 50-52 aluminum, it's really strong. Again, it has a much better retention. If it gets hit, it springs back, right? Where 3003, if it gets hit, it kind of bends and forms, right? It's gonna hold that shape. So you'll see higher strength applications. It could be even for tanks. This is a 50-52 tank with all 60-61 fittings on it. Okay, so depending upon the application, you may want some of that higher strength aluminum. 60-61, we already talked about that. It's easily machined, but it's hard to form. So if I look at those examples, here is a 60-61 piece that I formed at only 72 degrees, and it's already stress cracking. Right? So you can see how that works. So not a good application for bending and forming. The 50-52 is much better. This is 50-52 bent at 90 degrees, and you can see that even though it's a stronger grade of aluminum, it will take that form, right? But 50-52 has a breaking point. This is 50-52 at 135 degrees, and it actually starting to stress crack. You're seeing stress fractures inside that bend area, right? So there's a couple ways that you can eliminate that or help that problem. One of the things that you can help that problem is working with the grain structure or the grain boundaries of the aluminum. But just like steel, there's grain structure to the aluminum, and you can figure out which way it's running. So what I'll do is show you a graphic. Here's your grain, what we call our grain direction. To find out what that grain direction is, I basically like to put the aluminum up to some sort of light, and you can kind of see as the aluminum is formed and rolled, it will align those grain boundaries into a direction. The aluminum is much stronger when you make the bend against the grain. So this 90-degree bend I made with 50-52, the grain direction is opposite of the bend. Does that make sense? This one, the one that's showing stress fractures, it was bent in the same direction as your grain boundary. So I can pass these around if y'all want to just look at them and hold them up to the light. You can kind of see, you know, I got to put my glasses on, but that's why I did this. I made the marks on it. It's my cheat sheet, right? So here is 50-52. It's bent at only 120 degrees, and even with the grain direction, I'm starting to show some micro cracking. So every material still has a limit. A couple of ways around that. One, you can increase your bend radius, right? You can make that a little bit more gradual. Sometimes that's not an option. So sometimes you want to anneal the aluminum. And annealing, what that does is it takes that temper, it takes that out, it makes it easier to form that aluminum. 3003 typically doesn't need to be annealed, but you can do it, and there's certain applications that I do anneal the 3003. And a good example of that is this is 3003 bent at almost 180 degrees with the grain boundary, right? So the bending it the wrong way, and I still have a nice bend. So normally I do not anneal 3003 material. The only time I do is if I'm going to be doing a lot of bending or working the material after welding. And every time you cold work the aluminum, it gets harder, right? And there's a limit that you can cold work the material before it finally says, okay, I'm going to crack. And so that's an opportunity where you'll want to anneal that material first if you know you're going to do a lot of cold working on it, because you have a much wider window before you reach that, before you hit the chip on the aluminum, right? Where it starts cracking. So if I'm just doing some typical easy bends, I won't anneal it. I'll just go ahead and bend it and form it. But if I know I'm going to do a lot of panel working, panel beating, English wheeling, any type of cold working like that, then I will anneal the material. So annealing 3003 is actually done at about 775 degrees. You heat it up to that temperature and then just go ahead and let it air cool. Okay, you will then remove the temper of the material. It'll be now basically a zero temper. It'll be easy to work with. 50-52, if you anneal it, it definitely helps, especially when you're bending with the grain structure. So you'll be able to increase those bends, go back to a little tighter radius if you anneal it. If you want to anneal 50-52, 650 degrees is the magic number. Again, you can just heat it up and let it cool, air cool. Some people really want that higher strength 60-61. You can get it in sheets. You can fabricate with it. But again, we already proved that it doesn't bend very nicely. So if you want to anneal 60-61, it kind of sucks because it has to be done in a much more controlled environment. So you want to take your temperatures, again, back up to about 750, 775, but you need to hold that for a couple hours. Longer if you're working with thicker materials. Then you have to do a controlled reduction in time, 50 degrees an hour until you get down to 500 degrees, and then you can let it air cool. That would be the proper way to get 60-61 back to a zero. Okay, does that make sense? So it's still kind of a pain. I still don't recommend doing a lot of fabrication with 60-61. partially because this is what you're going to have for your mechanical properties, and really I would just not anneal it. I would do a special order of 6061O or 6061 zero temperature. Does that make sense? You can get that, but keep in mind your 6061O versus the standard 6061 T6. Our hardness will go from 95 for the T6 to 30, right? No problem. This is what we're looking for when we're talking about our fabrication of that. We're going to bend it, we're going to form it, we might want to hammer it, whatever. Our elongations is only going from 10 to 20. So you're still not gaining a whole lot. So it's still not ideal as a fabricating alloy, right? Our shear strength went from 30 to 12. Tensile strength went from 45 to 19 on ultimate, and our yield strength from 39 to 11. So it still is strong, but not ideal to form. And if you do want to form it, you're going to have to go up to 6 times the material thickness to make your bends. And make your bends gradually and make them slow. Okay. Filler metal selection. This is a key component to welding aluminum because if you pick the wrong stuff, you could possibly have cracking scenarios. And I see it a lot, and I'll tell you where in a minute. So if you go on your app store or whatever, and you can look up the Hobart Weld app. The Hobart Weld app is an excellent source for figuring out the filler material you need for different alloys. So when I select that filler metal, this is your home screen. I'm going to select aluminum, and then I'm going to get 2 scrolling selectors here. I can scroll up and select all these different alloys. And you can mix and match it, and it'll tell you what the best filler metal is based on the application. And there's a number of different points of the criteria, right? So in this case, I selected A356. A356 is a common casting, transmissions, cylinder heads, things like that. So this is what it tells me the filler metal selections are for this material. These are the filler metals it recommends. These are your application criteria. Okay, I got cracking, strength, ductility. I got corrosion resistance, which is basically anything that's going to be used in water, salt water, or regular water. Not chemical corrosion. That's not part of this. This is just strictly water or salt water applications. Then I have temperature and color, post-weld heat treat, which really only applies to the 7000 or your 6061s, right? And toughness. So I already said I'm going to take this casting and I'm going to call it a cylinder head. So my best filler metal to select here is going to be the A356. Most of the time you have to special order it. Most people don't carry it. Or I could get into what I would consider a second best opportunity would be the 4943. The reason I say that is because when I'm in the temperature category, that's my key indicator here. I'm not worried about strength at this time, is I'm making sure that that application can handle the higher temperatures. Do you know what the classic high temperature application is for aluminum? What is considered high temp in aluminum? Anyone who guess? Richard, you probably know this. No? What's the 800? That's a pretty good guess. Okay, aluminum itself, depending upon the alloy, melts between 1200 and 1600 degrees. Anything with a sustained temperature of over 150 degrees F is considered high temp. And the service temperature for most aluminums is ideally going to be between that 150 up to 500. The reason I say that is because you start getting higher or closer to that 600, 650 mark. Now you're getting to the point where some aluminum will be annealed. So you're going to be losing all that strength, right? So 500 degrees and less, typical on temperature, right? That's going to be ideal. So what happens if you exceed that temperature? A lot of times that weld filler metal that you've chosen will crack or start to disengage from the base metal. So that's going to be my key component when I'm going to select engine parts, things like that. Okay, and again, the next one I'm going to look for is strength. So depending upon the application, but that's why I love this A356 for doing this A356 casting. The next one I chose is 3003 to itself. Okay, so some of these tanks, this is 3003 to itself. Again, that tank, power steering, obviously temperature is over 150. Temperature is going to be my key indicator first. Okay. Second, I would go under strength, because now a power steering tank typically isn't pressurized, but some tanks like the overflow expansion tanks, those are. So I would probably, in this case, I'd be selecting a 4943. You'll see a lot of times in this selector, the 4043 and the 4943 together, they can pretty much interchange. But what I like about the 4943 is it's about 30% stronger than 4043. So that is an excellent option instead of the 4043 if you need a little bit more strength. Okay, so that's what I would pick in this application. 5052. Okay, I like 5052, and one of the things you're going to see on filler metal selections with 5052 is we've got this color chart here now. If you're sending something out to be anodized, or it's strictly for, you like the parts to look good, you're going to finish it off, you need a filler metal that can be color finished similar to the base metal. And anything in the 4000 series filler metals, it won't color match with the 5000 series filler, or the base metal. What'll happen is your welds will be a completely different color than the filler metal. It's amazing. So anything with an A rating will have basically the same color match as your base metal. So the problem with that is, if I'm building a tank or something that also has to have a high temperature application, look at the limitations of my filler metal. I only have basically two choices. So at this time, I would probably pick either the 5554 or back up to the 4943. You'll see that most of the stuff that I build out of aluminum, I leave natural. I don't anodize it, so I really don't worry about color. But hey, we're at SEMA, right? We got show cars. They like stuff pretty, so they might be looking for color. So any questions so far on that? Does that make sense? Yeah? Okay, let me do another one here on the 6061. 6061, again, we talked about it, very easily machined, but we also get a lot of guys use 6061 tubing for their turbo stuff. Charge tubes, heat exchangers, right, things like that. This is where I see a lot of people pick the wrong filler metal, because a lot of people have a misconception that the 5000 series filler metals are stronger than the 4000s. And in some applications that is true. But in this application, because you're in a hot environment and you're under pressure, especially on the turbocharged tubes, they're picking this 5356 filler metal, and look at the temperature rating. It's not even on the scale. So when you get these people who are always complaining about cracking of their turbo tubes, things like that, chances are they used the 5356, and they might have used it because when TIG welding 5356 to 6061, you get a nice shiny weld bead. It looks good. And again, our misconception in the industry is if it looks good, it's got to be strong, it's got to be right. That's not true. So definitely this application, this app, will get you in that better category of picking the filler metals. So I'm going to do another example here. I'm going to do a real wide range, right? 6061 to 3003, which is done a lot. All these fittings, all my fittings on my tank, that's what it is. 6061. 6061 is great because there's a lot of filler metals that it works well with. So in this application, again, I'm picking temperature first. One of the things you can look at is cracking. Cracking is the hot cracking. In other words, after you welded it, some filler metals are crack sensitive. So anything with an A rating means that once you weld it, it's not going to try and crack itself or pull itself apart. If you weld it, there are certain applications where you could get a quench crack sometimes as the weld is cooling. It tends to basically split itself apart. So anything with an A rating helps that. So again, anything with A rating, I'm going with the 4943 on this one again. Again, I like that little higher strength. It's a little bit more money than the 4043. The 4043 again is what I would call, that's like O positive blood. That's your universal donor, right? So if you don't know what it is, you don't know what the alloy is, that 4043 would probably be the choice, right? So, but that's going to be one of those things. Let me talk a little bit about machine settings. I know you've seen this part. So machine settings, thanks. On my machine settings, when we do certain welds, all of our, well, even back in the 70s, we developed a square wave technology. We had the ability to change the balance but not the frequency. When the inverters came along, we make that AC artificially, so we can make it whatever we want. So what balance does, it controls the oxide cleaning. It helps clean that oxide off the aluminum so you can weld it. The oxide layer is what gives the aluminum its corrosion resistance. It gives it a little bit of strength, but it's only a few microns thick. But you have to remove that oxide before you can weld it, and best practice is to take a stainless steel brush it, acetone it, and kind of clean it, right? But you still need AC. The AC waveform chips it off so you can weld it. We can control how much of that happens. So at 50% of your AC wave, right, the positive side of the AC cleans the aluminum, the negative side welds it. So at 50%, I'm spending half of my power cleaning and half of it welding. This is what you get, is this real wide puddle with that white flaky look at the edge of the weld. That's your cleaning zone. You clean this much aluminum, but you only welded this much, right? So what I like to do on the new machines is you can basically dial that in. I can adjust that balance to tighten up my cleaning zone. You still want to see it. You don't want to have it really wide, but you want to make sure you see it so you're cleaning enough aluminum so that the edges of the weld, which are called the toes, we want the toes to form smoothly into the base metal. When you're welding and you kind of see some speckling, like somebody's over your shoulder dumping pepper into your weld puddle, a lot of that is because some of the oxide is floating into the weld puddle. Okay, so you might not have had your balance set right. You're not cleaning enough. So at the factory, they call this the Pro Set. I call it the factory default. So they like to call it whatever they want. But the factory default is 75, which means I'm cleaning 25, welding 75. That gives me a much tighter oxide cleaning area. So if I'm building a part and aesthetics is important to me, do you want a piece that has a real wide cleaning zone or something that's narrower where you're just more looking at the weld puddle? So for aesthetics reasons, the weld puddle itself will be still strong. Okay, I'm talking completely about the oxide cleaning. I would rather have something that looks more tight, right? So it also decreases your post-weld cleanup. If you're going to send that piece out to get anodized and you have a real wide white etching, you got to do some material prep there, or that white etching material isn't going to color match as well as the base metal. Okay, so that's one way you can fine-tune these inverter-based machines, is your balance. The other way is with frequency. Frequency focuses the arc. The higher the number, the tighter the arc becomes. The lower the number, the wider and lazier it is. So if any of my experienced welders, right, of us older guys, have worked with the older transformer machines, a transformer machine gives you 60 hertz power. It can't change it because that's what it's plugged into the wall. And it's magnetically coupled to the primary. So if you feed a transformer 60 hertz, it gives you 60 hertz. So you get this real wide fluttery arc. Hard to control. So wide fluttery arc, not real deep penetration. Just by turning the frequency up, doubling it, 120, look what happened to the penetration. And look what happened to the focus. So now I got a lot more precision in my work, all right? And I'm not worried about that fluttering. If you try to weld inside this included area with a 60 hertz machine, what's going to happen?
It's going to jump all over.
Yeah, it's going to jump all over the place, right? And you'll end up, the arc wants to melt the sides of the piece before getting into the root. So now you just got to over weld it to make that happen. So what I do in this, because this is fairly tight, I would probably turn my frequency up to about 200. Yeah, and that would tighten it up, and I'd be able to pinpoint that right down into that weld joint. Yeah, so I can get that thing so tight that I could put a weld bead on this edge and not even hit the other side. That's, I'm sorry, I should have grabbed that from you before. So yeah, you can get it that tight, literally by dialing that precision up. So that's why people love DC TIG welding, because the arc goes exactly where they want it. The arc is pinpointed, it's DC, it doesn't change, it doesn't fluctuate. So TIG welding steel, a lot of people think is easier than aluminum, because it goes where you want it to go, right? So now we have that high precision just by adjusting that frequency. Okay, any questions? No? You guys are an easy group.
So with the balance settings, like what starts to make it impossible to weld? Like if you're so you're saying 50%. Like my machine has like a negative and a positive on my balance instead of like a percentage.
Yours has what?
It's like a negative and a positive, so like it'll be like -1, -2, -3.
Oh, okay. So your machine, is it a synchrowave or something, or?
It's a Lotus, but it's an inverter.
Okay, it is an inverter.
Yeah.
Okay, yeah. So I'm guessing when they're saying it's when minus or plus.
Yeah.
So I'm thinking that, and I don't know for sure, but I would think the minus would be more It's a Lotus, so it's see, this is where the terminology and definitions happen, right? Because some people identify, when we designed this back in the 70s, balance was a percentage of the weld time, the electronegative. So we express it as a percentage of the penetration cycle. So in other words, if I want more cleaning, I actually have to turn the number down. So I have to reduce the number. If I want less cleaning, I turn the number up. But because we have tended to talk about this adjustment in the terms of cleaning the oxides rather than penetration, a lot of companies now term that as a cleaning adjustment. So they say turning the number up gives you more cleaning. So it's opposite. I find that more with imported machines, things like that. They tend to express that backwards. I call it backwards because we developed it. Right, yeah. We were the first ones, 1979. Right? It's ours. We'll call it what we want. But that's what it is. So I'd love to say I know, but I don't know when you go minus and plus if which one is which. You'd basically, it's easy to do. You don't need to add filler. Run a bead on it all one negative, run it all the way positive, and just see what the width of the arc does. Yeah, that's what I would do. Yeah, excellent question though. So here's an example of that cleaning zone. I put this up here because I would have probably turned my balance number up to reduce the cleaning a little bit on this application. It would have made it look better, right? Make sense? And this is going to be an example of a 3003 brake venting 6061 tube, but there's some tight areas here. This one doesn't have a complete fusion. So they're trying to get the TIG torch in here, and you can see how wide the weld puddle was. I would have turned my frequency way up at that point, all right? Turn it up higher so I could get down, right? So I could get down into this tight area. Obviously that wasn't done here. So that's a good example of where they kind of missed that fusion point. So, that makes sense?
How would you actually get to that spot? You would turn it up, but you would use like...
Yeah, so, yeah, you could do that, yep. Yep, so you turn it out, pull the tungsten out, use a gas lens because that gives you a deeper gas coverage. Yep. Yep. So yeah, and here, and plus at this point, one of the cool things about that too is you don't have to come straight down at it. You can come a little bit off the side. And what I do is if I was welding this, I'd come off the side and come in with my filler metal on the other side. Yep. Yeah. So exactly. So that's kind of what we're working with. But even these smaller, like the Multimatics, they have what I would consider this. I use this machine basically probably 90% of the time. Now you can get into the Dynasties and they have the same adjustments, but they have a much broader range. So like on this machine, the Multimatic, we have it set, you could do it in auto set. So if I come down here and select TIG aluminum. The auto settings is going to basically default to the pro settings. It's going to give you 75 on the balance and 120 on the frequency. But that's a great starting point for people learning because they don't have to like mess with the settings. They can get themselves into a weldable condition and then worry about technique, right? But if you want to do those adjustments, all I got to do is take the auto set or the auto set off. Now I have frequency adjustment and balance control. So now I can adjust those things and fine tune those to your application. So even in, and I hesitate to say this is an entry level AC machine because it's not. Like our diversion models, again, they don't have those adjustability, but this machine, MIG welds, TIG welds, and stick welds, but the cool part about this one, it does it on AC as well. So a lot of companies can do the DC part of TIG, but when you get into this type of machine where you want to do AC, you actually have to put another inverter in it. You got to take the DC, turn it back into AC, and that part of the process is a lot more expensive because now you're on the high power circuit, the high current circuit, so the transistors and things needed to re-invert it back into welding AC are much larger. So, yeah. Cool. Any questions? You didn't record that whole thing, did you? Yeah. Oh, damn. So, cool. No questions at all? Is that a water pump? No, that's actually a fume extractor. Okay. Yep, so it's a small portable, runs on 120 power. It's totally variable speed, so you can control the suction. Yep, and so we just run it up to the bench. Yep. You good? No question? Yeah, there's a big filter canister in there that's, you can clean it or replace it. Yep. The neat thing about that is, yeah, it's really quiet. So I mean, it's been running. I mean, if I turn it wide open, now you can hear it, but it'll suck the weld wire out of your gun, right? You know, so. You know, I run it about a third of the way usually, but yeah, but it's quiet. I mean, it's got power like a shop vac, but it's quiet. That's cool. Yeah.
Is it like at max power? Does it take under your gas away?
Yeah, it would. Okay. Yes, yeah. So, you know, and if you're in like stick welding, the flux is melting in. You could turn that thing wide open and it's great for stick welding. So I would use that for that application. If I'm doing MIG and TIG, now you got to be a little bit more concerned. It's not like MIG isn't as bad because it's targeted a little bit more. TIG, it's definitely an issue, right? Because TIG welding, argon, it's heavier than air, it has a blanketing effect, and we want it to blanket there, right? Especially on certain alloys that are temperature sensitive, titanium especially. You gotta shield titanium until the weld puddle gets below 900 degrees, and that takes a while. So I don't, obviously, well, and you really should be doing titanium in a chamber or something where you have an argon envelope anyway. Yep. Good questions. Sweet.
I've had a lot of trouble with stainless, like some of the like exhaust tubes and stuff, like V-bend flanges, like get them too hot, or like passing the gas.
Okay.
Like that, like is that mostly like a lens thing or like a cup
Could
size?
be. Sometimes sometimes the cup size, sometimes it's flow rates. Sometimes I see people changing cup sizes and not adjusting their flow rates. Okay. So your flow rates are really going to be based on the orifice of that cup. So the bigger the orifice, the more flow you need. But I'll find people that will go down to say like a number 4 cup and they had a number 8 or a 7 on it. Now you have way too much force. So you have a lot of gas, but you pushed it down into an air like that, right? So it's like trying to weld with a fire hose. It's just way too much pressure and the arc becomes turbulent and it'll actually bounce off your workpiece and it'll swirl, it'll suck in more contaminants than it's pushing out. So too much pressure is just as bad as not enough. Yeah, so one of the things you can identify not enough flow is if your tungsten tip is starting to turn purple or black. Like if you get done welding and then you go to strike an arc, sometimes it'll cause the tungsten to contaminate, but you might get some hesitation on your arc starts. But really what you'll do is you'll see the point on the tungsten start to turn purple. That's an indication that you A, don't have enough flow, or B, you don't have enough post-flow time. So there's a lot of people that when they're TIG welding, they want to save a little money, they don't want 10 seconds of post-flow, they dial it down to 4. Well, now you're sacrificing your tungstens. So it's tit for tat, right? Yeah. So when I rather weld stainless, I use a big cup whenever I can. Another thing about big cups, they say, well, you can't get into some tight areas. Yes and no, but depending on the joint, a big cup, if I have a 1-inch cup, so if I'm using a cup like this, basically I can pull my tungsten out at least that far, and I'm still in the argon envelope. So yeah, I can get into those tight places really as long as you can see. Sometimes the application is tight and obstructed and you need a small cup so you can, so your head you can actually see the arc. But I use this style a lot, you know. But this style cup, I'm probably running sometimes 35 CFH. Yep, 35 CFH on something like that. Yeah. Now you can reduce that. They make a cup like this that's longer. I use almost a flush-mounted one because what it does is it tends to widen, right? It's kind of like a shotgun, right? Yeah, you change the choke in it so I get a little wider spread. So yeah, this is my different choke for a little wider spread of coverage. Yeah.
What's your, just a basic deal for Andy as far as the smaller cups, what size? How many CFMs?
Okay, so if I'm doing a number 4 without a gas lens, just a standard 4, I'm probably down at 8 to 10 max.
Right. And then a gas lens?
With a gas lens, you can even reduce it a little bit more because the flow is more efficient. So the gas lens takes the gas that's coming out of the cup that's normally turbulent because there's nothing to straighten it out. The gas lens runs it through that screen and makes it focused. So usually the gas lens is more efficient argon transfer, so you can lower your, you can lower your settings. So I'd run a number 7 without a gas lens at 22 with a gas lens, probably down to even 18 sometimes. That's what?
Say on aluminum?
Oh yeah, even on aluminum. Yeah.
So basically, every available chance you would use a gas lens rather than.
My motto, and that's just me. There's all kinds of way of doing stuff. Is there's no reason not to use a gas lens unless it's literally can't get in there. Now I have. I've got one of those quick change torches on my machine. There's sometimes I'm using a real small torch with there's no back cap on it, and I'm getting up behind in some of the roll cages in between the body or the side. Like if I got my A-pillar bar coming down and I got to weld the bay bar connector bar to it, the back side getting to that. Yeah, so there's no gas lens there. Yeah, so but if I can get at it, if I'm bench welding, it's got a gas lens on it. Yeah. No worries. Cool. Excellent. No more questions? All right, we're good. Thank you for your time.
Thank you.
Yeah.
Andy, what about using a pulsar for chromoly?
Oh yeah, I use a pulsar for chromoly a lot.
I'm just going to say.
Yeah, so chromoly is a temperature sensitive base metal. The more heat you put in it, the more potential it cracks. So yeah, the pulsar is great for that. I'll tell you another option if you want to, that I've been using lately. I've been building cars with Docol. Docol R8 is a high strength, low alloy steel. It has better operating characteristics than chromoly, and you can actually MIG weld it.
Yeah, because don't most of the NASCARs are all MIG welded.
Well, yeah, but they don't even use Docol. They use just mild steel DOM. So you still, depending upon the sanctioning body, so this Docol material was originally developed for the automotive market when cars started going away from full frames to unibody styles, right? And so they could take this Docol and stamp it, and they would make like their A pillar, C pillars, and B pillar bars out of it, and some of the floor structure, and it really started increasing crash ratings. And what the company who makes this material, they designed a way to precision roll it. They roll it and seam weld it. Okay, this is cool, right? So this is the only seam welded tubing that's approved by the NHRA in their top fuel classes. So Mfg, all these guys are building rail cars out of this Docol, and they're getting better fatigue life cycles. You know, you can only run that thing so often, and all of a sudden they crack in half, right? You guys seen that. So yeah, so what it is that fatigue life cycle is much better with this material. Another thing with chromoly is you gotta clean the weld joint. Like I take my emery cloth, I clean the weld joint, get all the mill scale off the chromoly. Otherwise your welds kind of look dirty. They don't look shiny. But if you take take emery cloth and clean every weld joint before you weld it, and then acetone clean it, the Docol, you don't have to do that. The Docol tubing on my rack looks like stainless steel. You take it, you wipe it off, you weld it, and it forms like chromoly. When I put it in my bender, it has a good amount of spring back, so you're going to have to calculate that like you do chromoly. The other thing that's great about that is because it was originally designed for the automotive market, it had to be able to be welded with most processes, so it includes MIG or TIG. So when I'm welding the Docol to itself, I TIG it, and most sanctioning bodies in those higher speed classes require that anyway. But when I'm putting my Docol to the frame doublers, or I'm welding it to the inside of the car, that's a mild steel frame doubler, I just MIG it. Yeah, so yeah, it's perfectly acceptable. But you can't do that with chromoly.
You're using acetone in a dust.
Yeah.
For aluminum and for steel.
Sure. Yeah. And most of the time, like for the steel, really all I'm doing is removing any parent metal oils that were on it. You know, I'm just cleaning it. That's all I'm doing with it. There's no oxidation on the Docol, but I've come to start using it more and more often. It's easier to work with. Like I say, it's got better life cycles, and yeah.
How about cleaning the rod before you use it?
Oh yeah, like your aluminum filler rod. Yeah, I don't tend to clean my steel stuff because I keep it in tubes anyway. But the aluminum stuff I do.
Use acetone?
I do, yeah. Yeah, you acetone or denatured alcohol. Acetone's easier for me to get, but yeah.
Of course, it's gotten a little weaker in
It's got what?
It's gotten a little weaker in its concentration.
Yeah.
In certain states, especially.
Oh, is that right? I didn't know that.
Yeah.
They actually have a percentage that they're allowed?
Well, they don't talk about it. They just don't give you as good a product.
That's crazy.
And it is.
Wow.
Crazy would be an understatement.
It's the full rod for Docol to mild steel.
You could do either the 80 SD2, which is kind of what I prefer. I go to that a lot. It's a higher strength filler. But on the one to mild steel, you could still use the 70 S2 filler metal for that. Yeah. So either one, really. I use the 80 SD2 when I'm doing the Docol to Docol. Yeah, we've done. Well, and DOM is still seam welded tubing. A lot of people don't know that. It's seam welded tubing that's drawn over mandrel, and it's smashed down so hard you can't tell it's there unless you look inside the tubing. But yeah, right. But even still, but this is natural seam welded, not drawn over mandrel, Docol tubing, approved for NHRA use. So it's great. Yeah, it's good stuff. It's what?
It'd be nice if it was more available.
That is true. I order mine 100 feet at a time because it comes out of Indiana. Yeah. No, the Docol. You've used it? Oh yeah. So I think as more people start using it, they'll be forced to open up some more distributors of it. So right now there's only really a couple, but the one primer one is out of Indiana, and but they're easy to work with, and they ship it. So yeah, but to make shipping worthwhile, I buy 100 feet of it. Yeah, and I mean, just so full disclosure, it is more money than chromoly, but it's easier to work with. You don't have to prep the joint before you do it, you know. So it's time versus material for me. That's why I like it. So.